We think of the Big Bang as the beginning of everything: space, time, matter, energy. But what if it wasn't the first? What if the universe has exploded into existence before and could do it again? Picture this: 13.8 billion years ago, everything we know burst into existence from an unimaginably hot, dense point smaller than a proton. Space itself began expanding faster than light could travel. Matter formed, stars ignited, galaxies swirled into being, and here we are today, floating on a pale blue dot in this vast cosmic ocean. But here's the mind-bending question that keeps cosmologists awake at night. Was this really the beginning, or just the latest reboot in an infinite series of cosmic restarts? Could the universe be like a phoenix, dying and being reborn again and again throughout eternity? From the cutting-edge theories of cyclic cosmology to the mysterious mathematics of quantum gravity, we're about to explore one of the most profound questions in all of science. Could the Big Bang happen again? And if so, what would that mean for everything we think we know about existence itself? The evidence we'll examine might surprise you. Some scientists claim they can see hints of previous universes in the cosmic microwave background radiation, the afterglow of our own Big Bang. Others propose that what we call the beginning might actually be a bounce, a cosmic rebound from a previous universe that collapsed into a point so small that space and time themselves were crushed out of existence, only to spring back to life in a new Big Bang. We're living in what might be just one chapter of an eternal cosmic story, where universes are born, grow old, die, and are reborn in an endless cycle that has no beginning and no end. The universe's reset button might not just exist, it might be pressed over and over again throughout all of eternity. So buckle up as we journey through the deepest mysteries of space, time, and the very nature of reality itself. By the end of our cosmic adventure, you'll never look at the night sky the same way again. The stars above might not just be the remnants of our universe's birth, they might be hints of universes that came before and clues to universes yet to come. Welcome to the science of cosmic reboots, where the end is just another beginning waiting to happen. To understand whether the Big Bang could happen again, we first need to grasp what actually happened 13.8 billion years ago. The Big Bang theory isn't just some wild guess cooked up by scientists with overactive imaginations. It's one of the most thoroughly tested, rigorously examined, and spectacularly verified theories in all of science, backed by decades of painstaking observations, elegant mathematics, and mountains of evidence that would make any detective jealous. But here's where things get fascinating and counterintuitive. The Big Bang wasn't an explosion that happened somewhere in the vast emptiness of pre-existing space. This is probably the biggest, most persistent misconception people have about the beginning of our universe, and it's a misconception that Hollywood movies and popular culture have unfortunately reinforced over and over again. There was no empty cosmic void where suddenly a massive bomb went off, scattering matter and energy in all directions like some sort of ultimate fireworks display. Instead, the Big Bang was something far more mind-bending and profound. It was the expansion of space itself, the very fabric of reality stretching and growing from an initial state of infinite density and temperature. Imagine you're an ant living on the surface of a completely deflated balloon, so flat that it's essentially two-dimensional. Now picture that balloon being inflated at an absolutely incredible rate, faster than you could ever imagine. From your tiny ant perspective, every other ant on the balloon's surface appears to be moving away from you, and the farther away they are, the faster they seem to be receding. But they're not actually flying through the balloon's surface. Instead, the surface itself is stretching and expanding, carrying everything along with it. That's essentially what happened to our universe, except instead of a two-dimensional balloon surface, it was three-dimensional space that began expanding from a state so dense and hot that our normal concepts of physics completely break down. We're talking about a state where the four fundamental forces of nature were unified into a single superforce, where the distinction between matter and energy had no meaning, and where quantum effects dominated everything at scales both infinitesimally small and cosmically large. In the very first moments after the Big Bang, during a period cosmologists call the Planck epoch, the universe was unimaginably hot and dense. We're talking about temperatures of 10 to the power of 32 degrees Kelvin and densities of 10 to the power of 96 kilograms per cubic meter. To put that temperature in perspective, the core of our sun, which seems incredibly hot to us, is only about 15 million degrees Kelvin. This primordial fireball was trillions upon trillions upon trillions of times hotter than the center of our nearest star, so hot that the very concept of temperature starts to lose its meaning. During the first infinitesimal fraction of a second, something absolutely extraordinary happened that changed the entire course of cosmic history. Scientists call it cosmic inflation, and it's one of the most important and dramatic events that ever occurred. Space itself expanded exponentially, growing by a factor of at least 10 to the power of 26 in just 10 to the power of negative 35 seconds. Let me repeat that because it's almost impossible to grasp. The universe grew from smaller than a proton to roughly the size of a grapefruit in an instant so brief that light, traveling at 300 million meters per second, couldn't even cross the width of a proton during that time. This period of rapid expansion wasn't just cosmologically significant, it solved several fundamental puzzles that had been bothering cosmologists for decades. It explained why the universe appears so remarkably uniform in temperature when we look at the cosmic microwave background radiation. Without inflation, different regions of the observable universe would never have been in thermal contact with each other, so there's no reason they should have the same temperature. Inflation stretched a tiny region that was in thermal equilibrium to cosmic scales, explaining this uniformity. Inflation also explained why the geometry of space appears to be perfectly flat rather than curved like the surface of a sphere or a saddle. Just as inflating a balloon makes any small section of its surface appear flat, cosmic inflation stretched space so much that any initial curvature was flattened out beyond our ability to detect it. But perhaps most importantly for our story about cosmic cycles, inflation set the stage for everything that followed by creating the tiny quantum fluctuations that would eventually become galaxies, stars, planets, and life itself. During inflation, quantum mechanical uncertainty at the smallest scales was stretched to macroscopic proportions, creating the seeds of all cosmic structure. As the universe continued to expand and cool after inflation ended, the fundamental forces of nature began to separate out in a process cosmologists call symmetry breaking. It was like watching the ingredients of reality itself crystallize out of pure energy as the temperature dropped. First, gravity split off from the other forces when the universe was about 10 to the power of negative 43 seconds old. Then, the strong nuclear force separated from the electroweak force. Finally, the electromagnetic force and weak nuclear force went their separate ways. Each of these phase transitions released enormous amounts of energy and may have created exotic particles and fields that don't exist in our universe today. Some theories suggest these phase transitions could have created cosmic strings, magnetic monopoles, or other topological defects that might still exist as relics from the universe's infancy. Within the first few minutes after the Big Bang, the universe had cooled enough for something called Big Bang nucleosynthesis to begin. This is when the first atomic nuclei formed as protons and neutrons began sticking together, despite the intense heat and radiation trying to tear them apart. The process created primarily hydrogen and helium nuclei, with trace amounts of lithium and beryllium. The precise ratios of these light elements depend sensitively on the density of ordinary matter in the universe, the number of different types of neutrinos, and the rate of expansion during nucleosynthesis. When we calculate what these ratios should be based on our understanding of nuclear physics and compare them to what we actually observe in the universe today, the agreement is absolutely spectacular. We find that about 75% of ordinary matter is hydrogen and 25% is helium, exactly matching the theoretical predictions. This perfect agreement between theory and observation is one of the most compelling pieces of evidence for the Big Bang model. It's like finding a perfect fingerprint at a crime scene. No other theory has ever been able to explain why the universe contains exactly this mix of light elements, and the precision of the match gives us tremendous confidence that we understand what happened during those first few crucial minutes. But the universe was still far too hot for complete atoms to form. For the next 380,000 years, space was filled with a hot, dense plasma of atomic nuclei and free electrons all mixed together. Light couldn't travel very far in this environment because it kept bumping into and scattering off the free electrons, making the universe completely opaque, like trying to see through an incredibly thick fog. The temperature and density were dropping as space continued to expand. But it wasn't until the universe had cooled to about 3,000 degrees Kelvin that something momentous occurred. Scientists call this event recombination, though it's actually better described as the first time electrons and nuclei combined rather than recombined. As the temperature dropped below this critical threshold, electrons finally had low enough energy to be captured by atomic nuclei, forming the first complete atoms in cosmic history. This moment was absolutely crucial because it suddenly made the universe transparent. With electrons now bound to nuclei instead of flying around freely, light could finally travel through space without constantly scattering. The universe went from being opaque like a thick fog to transparent like clear air. The light that was released at this moment, about 380,000 years after the Big Bang, has been traveling through space ever since. But here's the amazing part. We can still see this light today. The expansion of the universe has stretched its wavelength from the visible light it originally was into microwave radiation, but it's still there, filling every cubic centimeter of space around us. This is the cosmic microwave background radiation, or CMB, and it's literally the afterglow of the Big Bang itself. When radio astronomers Arno Penzias and Robert Wilson first discovered this radiation by accident in 1965, while trying to eliminate noise from a radio antenna, they had no idea they were looking at the most ancient light in the universe. Their discovery was like finding the universe's baby picture, and it provided the final piece of evidence that convinced most scientists the Big Bang theory was correct. The cosmic microwave background is remarkably uniform across the entire sky, with a temperature of about 2.7 degrees Kelvin in every direction we look. This uniformity is exactly what the Big Bang theory predicts, and it's strong evidence that the entire observable universe was once in thermal equilibrium. But the CMB isn't perfectly smooth. When we measure its temperature with exquisite precision using satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory, we find tiny variations, differences of just a few hundred thousandths of a degree from place to place. These minuscule temperature fluctuations represent the seeds from which all cosmic structure would eventually grow. These ripples in the cosmic microwave background are actually quantum fluctuations that were stretched to astronomical scales during the period of cosmic inflation. They're like fossilized quantum mechanics, preserving the uncertainty principle from when the universe was smaller than an atom and imprinting it across the cosmic sky. Every galaxy, every star, every planet, and ultimately every living thing owes its existence to these primordial quantum fluctuations. The pattern of these temperature variations also tells us something profound about the geometry of space itself. The size and angular distribution of hot and cold spots in the CMB reveal that our universe is geometrically flat to extraordinary precision. This means that parallel lines will remain parallel forever. The angles of triangles add up to exactly 180 degrees. And space follows the rules of ordinary Euclidean geometry that we learned in school. This flatness is actually quite remarkable and improbable. In Einstein's theory of general relativity, the geometry of space depends on its total energy density. If the universe contained too much matter and energy, space would be curved like the surface of a sphere, and the universe would eventually collapse back on itself. If it contained too little, space would be curved like a saddle, and the expansion would accelerate so rapidly that matter could never clump together to form galaxies and stars. The fact that our universe sits right at the boundary between these two possibilities, with just the right amount of matter and energy to make space perfectly flat, seems like an incredible coincidence. It's as if someone carefully fine-tuned the initial conditions of the Big Bang to produce a universe where complex structures like galaxies, stars, and planets could form. But there's even more evidence for the Big Bang. When we look at distant galaxies through our most powerful telescopes, we see something remarkable. They're all moving away from us, and more importantly, the farther away a galaxy is, the faster it's receding. This relationship, called Hubble's law, after astronomer Edwin Hubble, who first discovered it in 1929, is exactly what we'd expect if space itself is expanding uniformly in all directions. The light from these distant galaxies is redshifted, meaning its wavelength is stretched to longer, redder colors by the expansion of space during its journey to us. We can measure this redshift with incredible precision using spectroscopy, and it gives us a direct measurement of how the universe has been growing over cosmic time. Perhaps most remarkably, we can use these observations to run the cosmic movie backward in time. By measuring how fast the universe is expanding today and how that expansion rate has changed over billions of years, we can calculate when everything must have been squeezed together into that initial, hot, dense state. This gives us the age of the universe, 13.8 billion years, determined with a precision of less than 1%. All of this evidence paints a beautifully consistent picture that has been tested and retested by thousands of scientists over decades. Our universe began in an extremely hot, dense state and has been expanding and cooling ever since. The cosmic microwave background radiation, the abundance of light elements, the recession of distant galaxies, and the formation of cosmic structure all point to the same inescapable conclusion. The Big Bang really happened, and it happened exactly when and how the theory predicts. But here's where our story becomes truly fascinating and profound. If the Big Bang could happen once, creating space, time, matter, and energy from what appears to be absolutely nothing, could it happen again? Could our universe be just one cycle in an eternal series of cosmic births, deaths, and rebirths? The very success of Big Bang cosmology raises these mind-bending questions about whether our cosmic beginning was truly unique, or whether it might be part of a much larger, perhaps infinite pattern of cosmic death and rebirth that stretches backward and forward through eternity. Now that we understand how our universe began, we need to confront one of the most profound questions in all of cosmology. How will it end? The answer to this question holds the key to understanding whether the Big Bang could ever happen again, because the fate of our universe determines whether cosmic cycles are even physically possible. For most of human history, people assumed the universe was eternal and unchanging. The stars seemed fixed in their positions, the sun rose and set in an endless cycle, and nothing appeared to change on cosmic scales. But we now know that our universe is dynamic, evolving, and headed toward one of several possible endings that would have seemed like pure science fiction just a century ago. The ultimate fate of our universe depends on a cosmic tug-of-war between two opposing forces. On one side, we have gravity, the attractive force that pulls everything together and tries to slow down the expansion that began with the Big Bang. On the other side, we have the expansion of space itself, which tends to spread matter and energy apart and make the universe larger and more diffuse over time. For decades after Edwin Hubble discovered that the universe is expanding, astronomers assumed that gravity would eventually win this battle. They thought the expansion would gradually slow down, come to a halt, and then reverse itself as gravity pulled everything back together in a cosmic collapse they called the Big Crunch. This seemed like the most natural and logical ending to the cosmic story. But in 1998, two teams of astronomers studying distant supernovae made a discovery that shocked the scientific world and completely changed our understanding of the universe's future. Instead of slowing down as everyone expected, they found that the expansion of the universe is actually speeding up. This was like throwing a ball into the air and watching it accelerate upward instead of falling back down. This accelerating expansion is driven by something we call dark energy, one of the most mysterious and poorly understood phenomena in modern physics. Dark energy appears to be a property of empty space itself, creating a kind of anti-gravity that pushes space apart rather than pulling it together. It makes up about 68% of all the energy in the universe, yet we have almost no idea what it actually is or how it works. The discovery of dark energy opened up multiple possible scenarios for how our universe might end, each more mind-boggling than the last. Let's explore these cosmic endings and see which ones might allow for the possibility of another Big Bang. The first possibility is called heat death, or the Big Freeze, and it's currently the most likely fate based on our observations. In this scenario, dark energy continues to drive the accelerating expansion of the universe forever. As space keeps growing larger and larger, galaxies become increasingly isolated from each other. Eventually, they'll be so far apart that light from one galaxy will never reach another. Within each galaxy, stars will continue to form and die, but the supply of hydrogen gas needed for star formation is finite. Over tens of trillions of years, all the stars will burn out and die, leaving behind white dwarfs, neutron stars, and black holes scattered throughout an increasingly cold and empty universe. Even these stellar remnants won't last forever. Protons, the building blocks of atomic nuclei, might eventually decay over timescales of 10 to the power of 34 years or more. If they do, all ordinary matter will slowly disintegrate into elementary particles and radiation. The universe will become a thin soup of electrons, positrons, neutrinos, and photons, growing colder and more dilute with each passing eon. In the very far future, even black holes will evaporate through a quantum process called Hawking radiation. The largest black holes, with masses billions of times that of our Sun, will take 10 to the power of 100 years to completely evaporate. When the last black hole finally disappears in a final burst of radiation, the universe will reach a state of maximum entropy, with energy spread as evenly and thinly as possible throughout space. This heat death scenario might seem like the ultimate ending, but it's actually not the most extreme possibility. If dark energy continues to strengthen over time, or if it's caused by something called phantom energy with unusual properties, we could face an even more dramatic finale called the Big Rip. In the Big Rip scenario, the expansion of space accelerates so rapidly that it eventually overcomes all the fundamental forces holding matter together. First, galaxy clusters would be torn apart as the space between galaxies grows faster than gravity can pull them together. Then, individual galaxies would be shredded as dark energy overcomes the gravitational bonds holding their stars in orbit. As the expansion continues to accelerate, solar systems would be disrupted, with planets flung away from their stars. Eventually, the expansion would become so violent that it would overcome the electromagnetic forces holding atoms together tearing apart every molecule, every atom, and finally, every subatomic particle in the universe. Space itself would be ripping apart faster than the speed of light, destroying the very fabric of reality. The timeline for the Big Rip depends on the exact properties of dark energy, but some calculations suggest it could happen in as little as 22 billion years from now. That might seem like a long time, but it's less than twice the current age of the universe. In cosmic terms, it's practically tomorrow. But there's a third possibility that's far more relevant to our question about repeating Big Bangs. What if the expansion of the universe eventually stops and reverses itself? What if gravity ultimately wins the cosmic tug of war and pulls everything back together in a big crunch? For this to happen, something would have to change about dark energy. Currently, dark energy appears to have a constant density, meaning that as space expands, the total amount of dark energy increases proportionally. This is what drives the accelerating expansion. But what if dark energy isn't truly constant? What if it's a dynamic field that can change its properties over time? Some theoretical models propose that dark energy might be caused by a slowly evolving field called quintessence. Unlike the cosmological constant that Einstein proposed, quintessence can change its equation of state over cosmic time. If quintessence eventually changes from causing cosmic acceleration to causing cosmic deceleration, the expansion could slow down, stop, and reverse. In a Big Crunch scenario, the universe would essentially run the Big Bang in reverse. As space contracts, galaxies would be pulled closer together, eventually merging into larger and larger structures. The cosmic microwave background radiation would be blue shifted to higher and higher energies as space compressed around it. As the contraction continues, the universe would become hotter and denser. Stars would be torn apart by tidal forces, their material compressed into an increasingly hot and dense plasma. Eventually, the temperature would become so high that atomic nuclei would be broken apart. And finally, even protons and neutrons would be crushed out of existence. The final moments before the Big Crunch would mirror the earliest moments after the Big Bang, but in reverse. The universe would approach a state of infinite density and temperature, a singularity where our current laws of physics break down completely. From our perspective, this would mark the end of space, time, and everything we know. But here's where things get really interesting for our story about cosmic cycles. What happens at the moment of the Big Crunch? Does everything simply end? Or could this cosmic collapse somehow trigger another Big Bang, starting the cycle all over again? The idea of an oscillating universe that bounces between Big Bangs and Big Crunches has captivated scientists and philosophers for decades. In this model, our Big Bang wasn't the beginning of everything, but just the latest rebound in an infinite series of cosmic expansions and contractions. The universe would be like a cosmic accordion, expanding and contracting forever through cycles that might last hundreds of billions of years each. Each cycle would begin with a Big Bang, proceed through a period of expansion and structure formation, much like what we observe today, then reverse into a Big Crunch that would somehow trigger the next Big Bang. Our universe, with all its galaxies, stars, and planets, would be just one movement in an eternal cosmic symphony. But there's a major problem with the simple oscillating universe model. Each cycle would have to deal with the issue of entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time in a closed system. This means that each successive cycle would start with more disorder than the previous one. If entropy keeps building up from cycle to cycle, the universe can't keep oscillating forever. Eventually, it would reach a state of maximum entropy where no more cycles are possible. This is like trying to bounce a ball on a surface that absorbs some energy with each bounce. Eventually, the ball stops bouncing and comes to rest. Some cosmologists have proposed solutions to this entropy problem. Perhaps the extreme conditions during the Big Crunch somehow reset the universe's entropy, wiping the slate clean for the next cycle. Or maybe the universe finds ways to export entropy to other dimensions or parallel universes, allowing the oscillations to continue indefinitely. Another possibility involves quantum mechanics and the uncertainty principle. At the moment of maximum compression during the Big Crunch, quantum effects might become so strong that they prevent the formation of a true singularity. Instead of collapsing to infinite density, the universe might reach some minimum size and then bounce back, creating what cosmologists call a big bounce rather than a big bang. Recent observations, however, suggest that the Big Crunch scenario is becoming increasingly unlikely. The accelerating expansion driven by dark energy shows no signs of slowing down, let alone reversing. Every measurement we make of distant supernovae, galaxy clusters, and the cosmic microwave background confirms that dark energy is pushing the universe toward eternal expansion rather than eventual collapse. But science is full of surprises, and our understanding of dark energy is still in its infancy. We don't know whether dark energy will remain constant forever, gradually weaken, or perhaps even change sign and become attractive rather than repulsive. The equation of state of dark energy, the relationship between its pressure and density, is one of the most important unsolved problems in cosmology. Current observations suggest that dark energy behaves very much like Einstein's cosmological constant, with a pressure that's exactly negative 1 times its energy density. But the precision of our measurements isn't yet good enough to rule out small deviations from this value. If dark energy is even slightly different from a pure cosmological constant, it could evolve over time in ways that might dramatically change the universe's ultimate fate. There's also the possibility that our current understanding of gravity itself is incomplete. Einstein's general relativity has passed every experimental test we've thrown at it, but it might break down on the larger scales where dark energy dominates. Some alternative theories of gravity naturally produce cosmic acceleration without requiring mysterious dark energy, and these theories might predict different ultimate fates for the universe. The stakes couldn't be higher. If the universe is headed for heat death, with eternal expansion and cooling, then our Big Bang was likely a one-time event that will never be repeated. The cosmos would be like a firework that explodes once in brilliant glory and then fades forever into darkness. But if the universe is cyclic, bouncing between big bangs and big crunches in an eternal rhythm, then our cosmic beginning was just one beat in an infinite drum that has been playing since before time began and will continue playing long after everything we know has turned to dust. The answer lies hidden in the properties of dark energy, the nature of quantum gravity, and the fundamental structure of space and time themselves. As we'll see in the next chapters, some of the most brilliant minds in physics are working to understand these cosmic mysteries and determine whether we live in a universe that dies once or one that's reborn again and again in an endless cycle of cosmic death and resurrection. The idea that our universe might be caught in an endless cycle of death and rebirth is one of the most captivating and audacious concepts in modern cosmology. It challenges our most basic assumptions about beginnings and endings, suggesting that what we call the Big Bang might actually be just the latest beat in a cosmic rhythm that has been playing for eternity. But proposing that the universe is cyclic is one thing. Building a scientifically rigorous theory that explains how these cycles could actually work is something else entirely. Over the past few decades, some of the world's most brilliant theoretical physicists have developed sophisticated models that attempt to make cosmic cycles not just possible, but inevitable. The earliest version of a cyclic universe was surprisingly simple in its basic concept. Imagine the universe as a cosmic pendulum, swinging back and forth between expansion and contraction. It would begin with a Big Bang, expand for tens of billions of years, while stars and galaxies form and evolve, then gradually slow down as gravity overcomes the initial expansion. Eventually, the expansion would stop and reverse, pulling everything back together in a big crunch that would somehow trigger the next Big Bang. This oscillating universe model had an elegant appeal. It solved the problem of what came before the Big Bang by suggesting that there was no beginning at all. Instead of a universe that popped into existence from nothing, you had an eternal cosmos that had always been cycling through phases of expansion and contraction. Each cycle would last perhaps 100 billion years, and there could have been an infinite number of cycles stretching back into the past. But as we learned in the previous chapter, this simple oscillating model faces serious problems. The biggest issue is entropy, the measure of disorder in the universe. According to the fundamental laws of thermodynamics, entropy can only increase over time in a closed system. This means that each cycle would begin with more disorder than the previous one, making the oscillations gradually fade away like a bouncing ball, losing energy with each bounce. In the 1980s and 90s, cosmologists tried various ways to solve the entropy problem. Some suggested that the extreme conditions during the Big Crunch might somehow reset the universe's entropy, essentially wiping the cosmic slate clean for the next cycle. Others proposed that entropy might leak out of our universe into extra dimensions or parallel realities, allowing the cycles to continue indefinitely. But none of these solutions were entirely satisfactory, and the discovery of dark energy in 1998 seemed to deal a fatal blow to traditional cyclic models. If the expansion of the universe is accelerating rather than slowing down, how could it ever reverse into a big crunch? The simple oscillating universe appeared to be ruled out by observations. However, just when it seemed like cyclic cosmology was dead, theoretical physicists began developing far more sophisticated models based on cutting-edge ideas from string theory and higher dimensional physics. These new theories didn't just resurrect the idea of cosmic cycles, they transformed it into something far stranger and more beautiful than anyone had previously imagined. One of the most influential of these new models is called the ekpyrotic scenario, developed by physicists Neil Turok, Paul Steinhardt, and their collaborators. The name comes from the ancient Greek word ekpyrosis, meaning conflagration or cosmic fire, which the Stoic philosophers used to describe their own cyclic universe theory over 2,000 years ago. The ekpyrotic model is based on the radical idea that our universe is actually a three-dimensional surface, called a brane, floating in a higher dimensional space. In string theory, fundamental particles aren't point-like objects but tiny vibrating strings, and these strings can be attached to membranes or branes of various dimensions. Our entire observable universe, with all its matter, energy, and forces except gravity, would be confined to one such three-dimensional brane. But we wouldn't be alone in this higher dimensional space. The ekpyrotic model proposes that there's another brane floating parallel to ours, separated by a tiny gap in the extra dimensions. Both branes are slowly moving through the higher dimensional space, and occasionally they collide with each other in cosmic crashes that create what we perceive as big bangs. Picture two vast, flat sheets floating in space, slowly drifting toward each other over billions of years. When they finally collide, the enormous energy of the impact gets converted into the hot, dense matter and radiation that fills our universe immediately after the Big Bang. The collision also imparts the initial expansion velocity that starts the next phase of cosmic evolution. After the collision, the two branes bounce apart and begin the slow process of approaching each other again. During this phase, which could last trillions of years, our brane universe expands and cools. Stars and galaxies form and evolve, and eventually dark energy begins to dominate and accelerate the expansion. Meanwhile, the parallel brane is moving through its own cycle, gradually approaching us for the next cosmic collision. The beauty of the ekpyrotic model is that it elegantly solves many of the problems that plagued earlier cyclic theories. The collision between brains naturally resets the entropy of both universes, because the enormous energy of the impact erases all the complex structures that had built up during the previous cycle. It's like shaking an Etch-A sketch to clear the screen before drawing a new picture. The model also explains why our universe appears to be flat and homogeneous. Just as two flat sheets colliding would produce a flat impact surface, the collision between flat brains creates a universe with flat spatial geometry. The collision also synchronizes the properties of the universe across vast distances, explaining why the cosmic microwave background has the same temperature in all directions. Perhaps most remarkably, the ekpyrotic scenario can generate the tiny quantum fluctuations that eventually become galaxies and cosmic structure. During the slow approach phase before each collision, quantum fluctuations in the brain positions get stretched and amplified, creating the density variations that we observe in the cosmic microwave background. But the ekpyrotic model isn't the only game in town when it comes to modern cyclic cosmology. Another fascinating approach comes from the brilliant mathematical physicist Roger Penrose, who developed a theory called conformal cyclic cosmology, or CCC for short. Penrose's theory is based on a deep mathematical insight about the nature of space and time. In general relativity, the geometry of space-time can be described using what mathematicians call a conformal structure, which captures information about angles and light cones, but not absolute distances or time intervals. Penrose realized that in the very distant future, when all matter has decayed and only massless particles like photons remain, the universe loses its sense of scale. In this far future state, there's no way to measure absolute time or distance because there are no massive particles to serve as clocks or rulers. The universe becomes conformally equivalent to the initial state just after the Big Bang, when temperatures were so high that all particles were effectively massless. This mathematical equivalence suggests that the end of one cosmic cycle could smoothly transition into the beginning of the next. According to Penrose's theory, our universe will expand forever, just as current observations suggest. All the stars will burn out, all the black holes will evaporate through Hawking radiation, and eventually only photons and other massless particles will remain in an increasingly cold and empty cosmos. But rather than ending in heat death, this final state becomes the initial condition for a new Big Bang in a conformally transformed space-time. The transition from the end of one aeon, as Penrose calls each cosmic cycle, to the beginning of the next happens through a mathematical transformation that rescales space and time. The infinite future of one cycle becomes the Big Bang of the next, creating an eternal sequence of cosmic epochs that Penrose believes has been repeating forever. What makes Penrose's theory particularly intriguing is that he claims to have found observational evidence for it in the cosmic microwave background radiation. He argues that certain circular patterns in the CMB are actually imprints left by gravitational waves from supermassive black hole collisions in the previous aeon. These Hawking points, as he calls them, would be the only traces of the previous universe that survived the transition to our current cosmic cycle. Penrose's claims about observational evidence have been highly controversial, with most cosmologists arguing that the patterns he identifies are more likely due to statistical noise or instrumental effects rather than remnants from a previous universe. The debate continues, but it highlights how modern cyclic theories are making testable predictions that could potentially be confirmed or ruled out by observations. A third approach to cyclic cosmology comes from loop quantum gravity, an alternative to string theory that attempts to describe the quantum nature of space and time. In loop quantum gravity, space itself has a discrete, granular structure at the smallest scales, like a three-dimensional mesh made of quantum geometry. This granular structure of space has profound implications for what happens during the Big Bang. Instead of allowing the universe to collapse to a point of infinite density, The quantum geometry of loop quantum gravity creates a natural repulsive force that prevents the formation of a true singularity. As the universe contracts toward what would classically be a Big Bang or Big Crunch, quantum effects become stronger and stronger until they halt the collapse and reverse it into a big bounce. The loop quantum cosmology models suggest that our Big Bang was actually a big bounce, the moment when a previous universe reached its maximum compression and rebounded into the expansion phase that we observe today. The universe would be like a quantum ball bouncing between phases of contraction and expansion, with each bounce creating what appears to us as a new Big Bang. These loop quantum gravity models make specific predictions about signatures that might be observable in the cosmic microwave background. The quantum bounce would imprint characteristic patterns in the CMB that differ from those predicted by standard inflation theory. Future observations with more sensitive instruments might be able to detect these quantum signatures and provide evidence for or against the bouncing universe scenario. All of these modern cyclic theories share some common features that make them far more sophisticated than the simple oscillating universe models of the past. They're based on well-developed mathematical frameworks, from string theory, loop quantum gravity, or differential geometry. They make specific, testable predictions about observable phenomena, and they address the fundamental problems that plagued earlier cyclic models, particularly the entropy issue. But they also raise profound new questions about the nature of reality. If the universe is truly cyclic, what does that mean for the concepts of beginning and end? Are we living in an infinite series of cosmic reincarnations, with each cycle creating new stars, planets, and potentially life? Could there be subtle differences between cycles, or does each one play out in exactly the same way? Perhaps most mind-bending of all, these theories suggest that the Big Bang wasn't the beginning of time, but just a transition point in an eternal cosmic process. Time itself becomes cyclic, with the far future of one universe becoming the distant past of the next. The universe becomes like an eternal phoenix, dying and being reborn over and over again in cycles that stretch infinitely far into both the past and the future. As we'll explore in the next chapter, understanding whether these cycles could repeat endlessly requires grappling with some of the deepest questions in physics. How does entropy behave across cosmic cycles? Can information be preserved from one universe to the next? And what would it mean to live in a cosmos where every ending is also a new beginning? The most profound question in cyclic cosmology isn't whether the universe could go through one cycle of death and rebirth. It's whether these cycles could continue forever, creating an infinite sequence of universes stretching endlessly into both the past and the future. To understand why this matters, we need to confront one of the most fundamental laws of physics and explore how it might behave in the extreme conditions of cosmic cycles. The law we're talking about is the second law of thermodynamics, which states that entropy, the measure of disorder in any closed system, must always increase over time. This isn't just an abstract mathematical principle. It's the reason why hot coffee cools down, why ice cubes melt, why machines wear out, and why we age. It's arguably the most ironclad law in all of physics, with no known exceptions anywhere in the universe. But if entropy always increases, how could cosmic cycles repeat forever? Each cycle would have to start with more disorder than the previous one, like trying to organize a messy room when someone keeps adding more clutter. Eventually, you'd reach a state of maximum entropy where no further organization is possible, and the cycles would grind to a halt. This entropy problem has haunted cyclic cosmology since its earliest days. In the 1930s, physicist Richard Tolman calculated that each cycle in an oscillating universe would be longer and reach a higher maximum temperature than the previous one. The universe would be like a pendulum swinging with ever larger arcs until it eventually stopped oscillating altogether. Even if the universe could bounce between big bangs and big crunches, it couldn't do so forever. But modern cyclic theories propose several ingenious solutions to this seemingly insurmountable problem. The key insight is that the extreme conditions during cosmic transitions, whether they're brane collisions, conformal transformations, or quantum bounces, might fundamentally reset the universe's thermodynamic properties in ways that allow the cycles to continue indefinitely. Let's start with the ekpyrotic scenario and its approach to the entropy problem. In this model, our universe is a three-dimensional brane floating in higher dimensional space, periodically colliding with a parallel brane to create what we experience as big bangs. The crucial insight is that these brane collisions don't just transfer energy between the branes, they also provide a mechanism for entropy to be reset or redistributed. During the collision phase, the enormous gravitational and electromagnetic fields generated by the impact can reach energy densities comparable to those just after the Big Bang. Under these extreme conditions, the normal rules of thermodynamics might break down or operate in fundamentally different ways. The collision could essentially scramble all the information and energy in both branes, creating a fresh start for the next cycle. Think of it like shuffling a deck of cards. No matter how ordered or disordered the deck was before shuffling, the shuffling process itself creates a random distribution that effectively resets the system's entropy. Similarly, the violence of brane collisions might shuffle the fundamental degrees of freedom in both universes, wiping out the complex structures and entropy buildup from the previous cycle. But there's an even more radical possibility. In higher dimensional theories like string theory, entropy might not be conserved the way we expect. Our three-dimensional brane could be leaking entropy into the extra dimensions, or exchanging entropy with other branes floating in the higher dimensional space. This would be like having a pressure release valve that prevents entropy from building up indefinitely in any single universe. Some versions of the ekpyrotic model propose that there are many branes in the higher dimensional space, not just two. These multiple branes could be colliding with each other in complex patterns, creating a vast network of interconnected universes that share entropy between them. What appears to be an increase in entropy in our universe might actually be a redistribution of disorder across multiple parallel realities. Roger Penrose's conformal cyclic cosmology takes a completely different approach to the entropy problem. In his model, the entropy doesn't get reset between cycles, it gets transformed in a way that makes it irrelevant to the next cosmic epoch. The key is understanding what happens in the very far future, when all matter has decayed and only massless particles remain. In this distant future state, the universe consists entirely of photons, gravitons, and other particles that travel at the speed of light. For such particles, time and distance lose their absolute meaning because they don't experience the passage of time in the same way that massive particles do. From a photon's perspective, it travels from emission to absorption instantaneously, regardless of how far it travels through space. Penrose realized that this timeless state at the end of one cosmic cycle is mathematically equivalent to the initial conditions of the next Big Bang. The conformal geometry of space-time allows for a smooth transition between the infinite future of one aeon and the beginning of the next, effectively making the entropy of the previous cycle irrelevant to the new cosmic epoch. It's as if the universe forgets its own past when it transitions between cycles. All the complex structures, the black holes, the galaxies, and the accumulated entropy from the previous aeon simply fade away into mathematical irrelevance as space-time undergoes the conformal transformation that bridges one cycle to the next. But perhaps the most elegant solution to the entropy problem comes from loop quantum gravity and its prediction of a big bounce rather than a big bang. In these models, the quantum geometry of space itself provides a natural mechanism for resetting entropy during the bounce phase. As the universe contracts toward what would classically be a singularity, the discrete quantum structure of space creates increasingly strong repulsive forces. These quantum effects don't just prevent the formation of a true singularity, they create conditions so extreme that all the information about the previous cycle's complex structures gets scrambled beyond recognition. The quantum bounce is like putting the entire universe through a cosmic blender. All the particles, fields, and space-time geometry get mixed and reorganized at the most fundamental level possible. When the universe emerges from this quantum blender and begins expanding again, it's essentially starting fresh with maximum entropy distributed in the simplest possible way. What makes this particularly interesting is that the quantum scrambling during the bounce might not be completely random. Quantum mechanics is probabilistic, not chaotic, which means that certain patterns and correlations from the previous cycle might survive the bounce in subtle ways. This could lead to what physicists call quantum memory effects, where traces of previous cycles leave their mark on the cosmic microwave background or other observable phenomena. Recent calculations in loop quantum cosmology suggest that these quantum memory effects could be detectable with sufficiently sensitive instruments. The polarization patterns in the cosmic microwave background, for instance, might carry signatures of the quantum state just before the big bounce. If such signatures are found, they would provide direct evidence not only that our universe bounced rather than banged, but also that cosmic cycles can repeat while preserving certain types of information across the transitions. Another fascinating possibility emerges from the holographic principle, one of the most revolutionary ideas in modern theoretical physics. This principle suggests that all the information in any region of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. If the holographic principle is correct, then the entropy of our entire observable universe could be encoded on its cosmic horizon, the boundary beyond which we cannot see due to the finite speed of light and the age of the universe. During cosmic transitions, whether they involve brane collisions, conformal transformations, or quantum bounces, this holographic information might be preserved or transformed in ways that allow cycles to continue indefinitely. The holographic principle also suggests that apparent increases in entropy might be illusory, reflecting our limited perspective rather than fundamental physical reality. What looks like increasing disorder from our three-dimensional viewpoint might actually be perfect order when viewed from the higher dimensional perspective where the holographic information is stored. But there's yet another possibility that pushes the boundaries of our understanding even further. Some theories propose that cosmic cycles might occur not just in time, but across multiple dimensions, or even multiple timelines. In these models, entropy doesn't build up within individual cycles, because each cycle takes place in a slightly different version of reality. Imagine a cosmic kaleidoscope where each turn creates a new pattern that's similar to but distinct from the previous ones. The universe might be cycling through an infinite number of slightly different configurations, exploring every possible way that matter, energy, and space-time can be arranged. In such a scenario, entropy wouldn't accumulate because each cycle would be unique, preventing the buildup of disorder that would eventually halt the oscillations. These multiverse versions of cyclic cosmology connect to some of the most speculative ideas in modern physics, including eternal inflation, the string theory landscape, and many worlds' quantum mechanics. They suggest that our observed universe might be just one thread in an infinite cosmic tapestry, with cycles occurring simultaneously across countless parallel realities. The observational consequences of these various entropy solutions are still being worked out by theoretical physicists around the world. Each model makes different predictions about what we should see in the cosmic microwave background, the distribution of galaxies, the properties of gravitational waves, and other observable phenomena. Some models predict that we should see subtle anomalies in the CMB that reflect the influence of previous cycles. Others suggest that that certain types of cosmic structure should be enhanced or suppressed compared to what standard Big Bang theory predicts. Still others propose that we might detect gravitational waves with characteristic signatures that could only come from cosmic bounces or brane collisions. Perhaps most intriguingly, some cyclic theories predict that the fundamental constants of nature, things like the strength of the electromagnetic force or the mass of the electron, might vary slightly from cycle to cycle. If true, this could explain why our universe appears to be fine-tuned for the existence of stars, planets, and life. Rather than requiring a cosmic designer or an infinite multiverse, the fine-tuning could simply reflect the fact that we happen to live in a cycle where the constants took on values compatible with our existence. The implications extend far beyond physics into philosophy, religion, and our understanding of humanity's place in the cosmos. If cycles repeat forever, then every possible configuration of matter and energy will eventually occur an infinite number of times. This includes not just our current universe with all its galaxies and stars, but exact duplicates of our solar system, our planet, and even ourselves. In an eternally cycling universe, you wouldn't just live once. You would live an infinite number of times, in an infinite number of slightly different versions of reality. Every choice you make, every word you speak, every thought you think would be repeated endlessly across the cosmic cycles, along with every possible variation of your life that quantum mechanics and chaos theory allow. This prospect might seem either comforting or terrifying, depending on your perspective, but it highlights just how radically cyclic cosmology challenges our conventional notions of time, causality, and individual existence. In a universe that dies and is reborn forever, the concepts of beginning and end lose their meaning, replaced by an eternal present that encompasses all possible pasts and futures. As we'll explore in the next chapter, recent observations of the cosmic microwave background and other astronomical phenomena are beginning to provide clues about whether these cosmic cycles are real or just mathematical fantasies. The universe itself might be telling us whether it's destined to die once and for all, or whether it's been dancing this cosmic dance of death and rebirth since before time began. At the heart of every theory about repeating Big Bangs lies one of the most profound questions in all of science. What happens when the universe reaches the ultimate extremes of density and temperature? When matter is compressed beyond anything we can imagine and space-time itself begins to break down, do the familiar laws of physics simply stop working, or do they transform into something entirely new and unexpected? To answer this question, we need to venture into the strange and counterintuitive realm of quantum mechanics, where particles can exist in multiple states simultaneously, where the very act of observation changes reality, and where the uncertainty principle ensures that nothing can ever be measured with perfect precision. When we apply these quantum rules to the entire universe, we discover possibilities that are both mathematically elegant and utterly mind-bending. The key insight is that quantum mechanics doesn't just govern the behavior of atoms and subatomic particles. At the moment of the Big Bang, when the entire observable universe was smaller than a proton, quantum effects would have dominated everything, including the structure of space and time themselves. Understanding what quantum mechanics predicts about these extreme conditions is crucial to determining whether Big Bangs can repeat. The traditional Big Bang theory, based on Einstein's general relativity, predicts that if we run the cosmic expansion backward in time, we eventually reach a point of infinite density and temperature called a singularity. At this singularity, the mathematical equations that describe space-time literally break down and give nonsensical answers like infinity divided by zero. It's a sign that our classical physics has reached its limits and that something new must take over. But quantum mechanics suggests that nature abhors these mathematical infinities. The uncertainty principle, which states that you cannot simultaneously know both the exact position and momentum of any particle, implies that there should be fundamental limits to how precisely we can compress matter and energy. At some point, quantum effects should become so strong that they prevent the formation of true singularities. This is where loop quantum gravity enters the picture as one of the most promising approaches to quantum cosmology. Unlike string theory, which attempts to replace particles with tiny vibrating strings, loop quantum gravity focuses on quantizing space and time themselves. It suggests that at the smallest scales, space isn't smooth and continuous like we experience it, but rather has a discrete, granular structure made up of quantum building blocks. Imagine zooming in on a photograph until you can see the individual pixels that make up the image. From a distance, the photo appears smooth and continuous, but up close, you discover it's actually composed of tiny discrete elements. Loop quantum gravity proposes that space itself has a similar structure, with fundamental units of volume that cannot be subdivided further. This quantum structure of space has revolutionary implications for cosmology. When we apply loop quantum gravity to the Big Bang, we discover that the classical singularity is replaced by something called a big bounce. As the universe contracts toward what would classically be infinite density, the quantum geometry of space creates an increasingly strong repulsive force that eventually halts the collapse and reverses it into a new phase of expansion. The bounce occurs when the universe reaches what's called the Planck density, about 10 to the power of 96 kilograms per cubic meter. This is the density at which quantum effects become so strong that they dominate over classical gravity. At this point, the quantum repulsion becomes stronger than gravitational attraction, causing the universe to rebound like a compressed spring suddenly released. What makes this particularly exciting is that loop quantum cosmology makes specific, testable predictions about what we should observe in our universe if it really did bounce rather than bang. The quantum bounce would leave characteristic imprints in the cosmic microwave background radiation that differ subtly but measurably from the predictions of standard inflation theory. During the bounce phase, quantum fluctuations in the geometry of space would be amplified and stretched, creating a distinctive pattern of temperature variations in the cosmic microwave background. These patterns would have specific mathematical properties related to the quantum nature of the bounce, including correlations that extend across larger angular scales than inflation alone would predict. The polarization of the cosmic microwave background provides another potential smoking gun for quantum bounces. During the bounce, gravitational waves generated by the quantum geometry would create spiral patterns in the polarization of the CMB photons. These patterns would be subtly different from those produced by gravitational waves during inflation, potentially allowing us to distinguish between bouncing and inflationary scenarios. Future observations with more sensitive polarization detectors might be able to detect these quantum signatures and provide direct evidence that our universe bounced rather than banged into existence. Several upcoming missions and ground-based experiments are specifically designed to measure CMB polarization with the precision needed to test these quantum cosmology predictions. But loop quantum gravity isn't the only quantum approach to understanding cosmic origins. Another fascinating possibility emerges from the Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe. This equation treats the universe like a quantum mechanical particle, with a wave function that describes all possible configurations of matter, energy, and space-time geometry. The Wheeler-DeWitt equation suggests that the universe might not have a single definite history, but rather exists in a quantum superposition of all possible histories simultaneously. From this perspective, the Big Bang isn't a single event, but a quantum transition between different possible states of reality. The universe could be constantly branching and merging between different quantum histories, with our observed reality being just one thread in an infinite quantum tapestry. This quantum superposition approach leads to some truly bizarre possibilities. The universe might be bouncing not just between expansion and contraction phases, but between entirely different configurations of physical laws, dimensions, and fundamental constants. Each quantum transition could reset not just the matter and energy in the universe, but the very rules that govern how reality operates. Another quantum cosmology approach involves applying the path integral formulation of quantum mechanics to the entire universe. In this framework, developed by physicists like James Hartle and Stephen Hawking, the universe is described as summing over all possible space-time geometries, weighted by their quantum probability amplitudes. The path integral approach suggests that the universe might have emerged from a quantum fluctuation in what Hawking called imaginary time. In this picture, the Big Bang represents a quantum tunneling event, where the universe tunneled from a state of nothingness into existence, similar to how particles can tunnel through energy barriers in quantum mechanics. But if the universe can tunnel into existence once, quantum mechanics suggests it could happen again. The same quantum processes that created our Big Bang could occur repeatedly, either in sequence or in parallel, creating multiple universes or multiple cycles of the same universe. The tunneling probability calculations suggest that these quantum creations could continue indefinitely, limited only by the fundamental structure of quantum mechanics itself. One of the most intriguing aspects of quantum cosmology is how it handles the concept of time itself. In classical physics, time is an absolute background against which events unfold. But in quantum cosmology, time emerges from quantum processes and might not have existed before the Big Bang or quantum bounce. This has profound implications for understanding cosmic cycles. If time itself is created anew with each bounce or tunneling event, then asking what came before the Big Bang becomes as meaningless as asking what's north of the North Pole. Each cycle would create its own temporal dimension, potentially allowing for infinite cycles without requiring infinite time. The quantum creation of time also suggests that causality might work differently in cyclic universes. Events in one cycle might not directly cause events in the next cycle, but rather, both cycles might emerge from the same underlying quantum process. It's like asking whether one frame of a movie causes the next frame. The frames are related, but their connection comes from the deeper structure of the film itself. Recent developments in quantum field theory have revealed another surprising possibility. Virtual particles, which constantly pop into existence and annihilate in empty space due to quantum uncertainty, might play a crucial role in cosmic cycles. Under extreme conditions, these virtual fluctuations could become real and drive cosmic transitions. During a big crunch or approaching a quantum bounce, the intense gravitational fields could amplify virtual particle production to macroscopic levels. The energy of these newly created particles could provide the driving force for cosmic expansion, effectively converting the gravitational potential energy of a collapsing universe into the kinetic energy of an expanding one. This virtual particle mechanism could create a natural cycle without requiring any external intervention or fine-tuning. The universe would be like a quantum engine, continuously converting gravitational potential energy into expansion energy through the production of virtual particles. The cycle would be self-sustaining, driven entirely by the fundamental properties of quantum mechanics and gravity. Quantum entanglement, the spooky action at a distance that Einstein famously criticized, might also play a role in cosmic cycles. If quantum information can be preserved across cosmic bounces or transitions, then each new cycle might retain entanglement correlations from previous cycles. This could create a form of cosmic memory that allows information to survive the apparent destruction and recreation of space-time. Some theories propose that the vacuum state itself, the quantum mechanical ground state of empty space, contains enough information to reconstruct entire universes. If this quantum vacuum remains stable across cosmic transitions, it could serve as a blueprint for regenerating complex structures in each new cycle. The universe would be like a quantum computer that stores its own program in the structure of empty space. The experimental verification of these quantum cosmology ideas presents enormous challenges. We can't create mini-universes in the laboratory or travel back in time to observe the Big Bang directly. But quantum cosmology makes specific predictions about observable phenomena that we can test with improving technology and more sensitive instruments. The cosmic microwave background remains our most direct window into the quantum processes that occurred during cosmic creation. Future observations might reveal the subtle signatures of quantum bounces, virtual particle production, or entanglement correlations that would confirm these exotic possibilities. Gravitational wave detectors like LIGO and Virgo are already beginning to probe the quantum nature of gravity on smaller scales. Future space-based detectors might be sensitive enough to detect the gravitational wave signatures of cosmic bounces or quantum transitions, providing another experimental window into quantum cosmology. Perhaps most excitingly, quantum cosmology suggests that we might be able to test these ideas using quantum computers and quantum simulators. By creating quantum systems that mimic the behavior of mini-universes, we might be able to study how quantum effects influence cosmic evolution and test whether quantum processes can indeed create self-sustaining cosmic cycles. The implications of quantum cosmology extend far beyond physics into our understanding of existence itself. If quantum mechanics allows for repeating Big Bangs, then our universe might be just one quantum fluctuation in an infinite sea of possible realities. The multiverse wouldn't just contain different universes existing in parallel, but different cycles of the same universe exploring every possible quantum history. In such a quantum cyclic cosmos, every possible variation of reality would eventually occur, including exact quantum copies of our current universe and ourselves. But unlike classical cyclic models where repetition is deterministic, quantum cycles would explore all possibilities, ensuring that no two cycles are exactly identical while guaranteeing that every possible cycle eventually occurs. As we'll discover in the next chapter, some scientists believe they've already found hints of these quantum cosmic cycles hidden in the patterns of the cosmic microwave background and other astronomical observations. The universe itself might be showing us the evidence we need to determine whether we live in a quantum cosmos that bounces, tunnels, and cycles through infinite possibilities, or whether our Big Bang was a unique quantum event that will never be repeated. The question of whether our universe could ever stop expanding and collapse back on itself isn't just academic speculation. It's one of the most important unsolved problems in cosmology today, with implications that reach far beyond theoretical physics into the very nature of reality itself. To understand whether cosmic cycles are possible in our universe, we need to examine the mysterious force that's currently driving our cosmic expansion and determine whether it could ever change its mind. Right now, as you're listening to these words, space itself is expanding at an accelerating rate. Every second, every cubic meter of empty space grows larger, pushing galaxies apart and stretching the very fabric of reality. This acceleration is driven by something we call dark energy, but despite decades of intensive research, we still have almost no idea what dark energy actually is or how it works. What we do know is that dark energy behaves very strangely compared to ordinary matter and radiation. Normal matter exerts gravitational attraction, pulling things together and trying to slow down the cosmic expansion. Radiation does the same thing, but with an additional pressure component that makes its gravitational effects even stronger. But dark energy does exactly the opposite. It creates a kind of anti-gravity that pushes space apart rather than pulling it together. This anti-gravitational effect isn't science fiction. It's a direct consequence of Einstein's equations of general relativity when applied to a substance with very unusual properties. For dark energy to cause cosmic acceleration, it must have negative pressure, meaning it pushes outward rather than inward. And this negative pressure must be so strong that it more than compensates for the positive energy density that would normally create gravitational attraction. The simplest explanation for dark energy is Einstein's cosmological constant, a term he originally added to his equations to allow for a static universe. The cosmological constant represents the energy of empty space itself, a kind of vacuum energy that has the same density everywhere and remains constant as the universe expands. Unlike matter, which becomes more dilute as space grows, the energy density of the cosmological constant stays exactly the same no matter how much the universe expands. This constancy is what drives the acceleration. As the universe expands and matter becomes more dilute, dark energy maintains its density and gradually becomes the dominant component. Today, dark energy makes up about 68% of all the energy in the universe, compared to just 5% for ordinary matter, and 20% for dark matter, 7% for dark matter. But here's where things get interesting for our question about cosmic cycles. The cosmological constant isn't the only possible explanation for dark energy. There are alternative models where dark energy can change its properties over time, potentially transforming from a repulsive force that accelerates expansion into an attractive force that could reverse it. These dynamic dark energy models involve what physicists call quintessence, named after the fifth element that ancient philosophers believed filled the heavens. Unlike the cosmological constant, quintessence is a field that can evolve over cosmic time, changing its energy density and pressure as the universe ages. The key parameter that determines whether quintessence causes acceleration or deceleration is called its equation of state, usually denoted by the symbol W. This parameter measures the ratio of pressure to energy density. For the cosmological constant, W equals -1, meaning the pressure is exactly -1 times the energy density. This specific value causes eternal acceleration. But if quintessence has W greater than -1, it could eventually stop accelerating the expansion and even reverse it. If W becomes greater than -1/3, the universe would begin decelerating. And if W becomes positive, quintessence would start behaving like ordinary matter, adding to the gravitational pull that could eventually halt expansion and trigger a big crunch. Some quintessence models predict that this transition from acceleration to deceleration could happen naturally as the field evolves. The quintessence field might be slowly rolling down a potential energy curve, like a ball rolling down a hill. Different parts of this curve could have different values of W, allowing the field to transition from causing acceleration to causing deceleration as it evolves. One particularly intriguing class of models involves phantom dark energy, where W is less than -1. Phantom energy has even more negative pressure than the cosmological constant, causing the universe to accelerate at an ever-increasing rate. But some phantom models predict that the field could eventually undergo a phase transition, flipping from phantom behavior to normal quintessence behavior. If such a transition occurred, the universe could go from super-accelerated expansion to deceleration in a relatively short cosmological time. The transition might even be triggered by the phantom field reaching some critical density or by interactions with other fields in the universe. Recent observations from Type 1a supernovae, galaxy clusters, and the cosmic microwave background have been trying to pin down the exact value of W and determine whether it's changing over time. The current data suggests that W is very close to -1, consistent with a cosmological constant, but the error bars are still large enough to allow for small deviations. The Planck satellite mission, which mapped the cosmic microwave background with unprecedented precision, found W equals -1.03 plus or -0.03. This is tantalizingly close to the cosmological constant value of -1, but not quite precise enough to rule out slowly evolving quintessence. Future observational programs are designed to measure W with even greater precision and determine whether it's truly constant or slowly changing. The Dark Energy Survey, the Large Synoptic Survey Telescope, and space missions like Euclid and the Wide Field Infrared Survey Telescope will map billions of galaxies and measure their distances and recession velocities with extraordinary accuracy. These observations will be sensitive enough to detect changes in W of just a few % over cosmic time. If dark energy is truly a cosmological constant, these measurements should confirm that W equals -1 to high precision. But if quintessence is responsible for cosmic acceleration, these surveys might detect the subtle signatures of field evolution. The implications are profound. If W is changing and could eventually become greater than -1/3, then our current phase of accelerated expansion might not last forever. The universe could enter a decelerating phase within the next few billion years, potentially setting the stage for an eventual big crunch and cosmic cycle. But even if dark energy remains constant, there are other mechanisms that could potentially reverse the expansion. Some modified gravity theories propose that Einstein's general relativity breaks down on the largest scales, and that the apparent acceleration is actually due to our incomplete understanding of gravity rather than mysterious dark energy. In these modified gravity models, the expansion history of the universe could be very different from what general relativity predicts. Some models naturally produce periods of acceleration followed by deceleration, creating cosmic cycles without requiring any exotic forms of matter or energy. String theory also offers possibilities for cosmic reversal through mechanisms involving extra dimensions and higher dimensional objects called branes. In some brane world scenarios, our universe is embedded in a higher dimensional space where the effective laws of gravity can change over time as branes move or interact with each other. The motion of branes in extra dimensions could alter the expansion rate of our universe in unpredictable ways. A brane collision or close encounter might suddenly change the effective value of dark energy, potentially reversing the acceleration and triggering a contraction phase. Another possibility involves the quantum nature of dark energy itself. If dark energy is fundamentally quantum mechanical, it might be subject to quantum fluctuations that could cause dramatic changes in its properties. Large-scale quantum fluctuations in the dark energy field could create regions where the expansion reverses, leading to local big crunches even if the overall universe continues expanding. These quantum dark energy models predict that our universe might be a patchwork of expanding and contracting regions, with some areas undergoing eternal expansion while others cycle through phases of growth and collapse. We might happen to live in an expanding region, but vast areas of the universe could be experiencing very different fates. The timescales involved in these scenarios vary enormously depending on the specific model. Some quintessence theories predict that the transition from acceleration to deceleration could happen within the next 10 billion years, roughly doubling the current age of the universe. Others suggest much longer timescales, with transitions occurring hundreds of billions or even trillions of years in the future. Phantom dark energy models that lead to the Big Rip scenario predict even more dramatic changes on shorter timescales. If the phantom field undergoes a sudden phase transition, the universe could flip from superacceleration to rapid contraction in less time than it takes for light to cross our solar system. But perhaps the most intriguing possibility is that our universe is already oscillating between expansion and contraction phases, but on timescales so long that we haven't noticed. If cosmic cycles last hundreds of trillions of years each, our current expansion phase might just be one brief moment in an eternal oscillation that has been going on forever. The observational signatures of such ultra-long cycles would be extremely subtle. We might see hints in the large-scale structure of the universe, unusual patterns in the cosmic microwave background, or anomalies in the distribution of dark matter that reflect the influence of previous cycles. Some cosmologists have claimed to find evidence for such signatures in existing data. Certain large-scale anomalies in the CMB, unusual alignments of galaxy clusters, and unexpected patterns in the cosmic web have all been interpreted as possible evidence for cyclic behavior. However, most of these claims remain highly controversial. The statistical significance of the observed anomalies is often marginal, and alternative explanations involving systematic errors, selection effects, or simple cosmic variance cannot be ruled out. The search for definitive evidence of cosmic cycles faces fundamental observational challenges. If the cycles are truly periodic, any signatures from previous cycles would be extremely diluted by the expansion of space and the passage of cosmic time. Detecting such faint signals requires extraordinary precision and careful analysis to distinguish genuine cosmic signatures from instrumental noise and systematic effects. Future gravitational wave detectors might provide new ways to probe the expansion history of the universe and search for signs of cosmic cycles. The proposed space-based detector LISA will be sensitive to gravitational waves from massive black hole mergers at cosmological distances, potentially revealing information about the universe's expansion rate throughout cosmic history. Even more ambitious proposals involve using quantum interferometry to detect the gravitational wave background from cosmic inflation or quantum bounces. These ultra-sensitive detectors could potentially measure the primordial gravitational waves that would be generated during cosmic transitions, providing direct evidence for or against cyclic models. The stakes couldn't be higher. If our current expansion can reverse, either through dark energy evolution, modified gravity, or quantum effects, then cosmic cycles remain a viable possibility for our universe. We might be living in just one phase of an eternal cosmic rhythm that has been playing since before time began. But if dark energy is truly a cosmological constant that will drive eternal acceleration, then our universe is headed for heat death, and our Big Bang was likely a unique event that will never be repeated. The fate of cosmic cycles hangs in the balance, waiting for the next generation of observations to reveal whether our universe is destined for eternal expansion or cosmic resurrection. As we'll explore in the next chapter, some scientists believe they've already found tantalizing hints of previous cosmic cycles hidden in the subtle patterns of the cosmic microwave background radiation. These potential signatures could provide the smoking gun evidence we need to determine whether we live in a cyclic cosmos or a universe that began once and will end forever. The cosmic microwave background radiation is like the universe's baby picture, a snapshot of how things looked when the cosmos was only 380,000 years old. But according to some of the world's most brilliant physicists, this ancient light might contain something even more extraordinary than we ever imagined. Hidden within its subtle temperature variations and polarization patterns could be the ghostly signatures of universes that existed before our Big Bang. Faint echoes from cosmic cycles that played out billions of years before our current universe was even born. The idea that we could detect traces of previous universes might sound like science fiction, but it's based on solid theoretical physics and increasingly sophisticated data analysis techniques. If cosmic cycles are real, then the extreme conditions during cosmic transitions, whether they involve quantum bounces, brane collisions, or conformal transformations, should leave characteristic imprints that we can potentially observe today. The most famous and controversial claims about pre-Big Bang signatures come from Roger Penrose, the Nobel Prize-winning mathematical physicist who developed conformal cyclic cosmology. Penrose argues that his theory makes specific, testable predictions about what we should see in the cosmic microwave background if our universe is indeed part of an infinite sequence of cosmic cycles. According to Penrose's model, the previous cosmic cycle, which he calls the previous aeon, would have contained supermassive black holes that gradually evaporated through Hawking radiation during the final stages of that universe's evolution. The evaporation of these black holes would have produced intense bursts of gravitational waves that propagated through the conformally transformed space-time transition between the old and new aeons. These gravitational wave bursts from evaporating black holes in the previous universe should have left their mark on the cosmic microwave background radiation in our current cycle. Specifically, Penrose predicts that we should see concentric circles of slightly enhanced temperature in the CMB, with each circle representing the cross-section of a spherical gravitational wave burst from a black hole evaporation event in the previous aeon. In 2010, Penrose and his collaborator Vahe Gurzadian published a paper claiming that they had found exactly these circular patterns in the Wilkinson microwave anisotropy probe data. They identified dozens of concentric circles with the statistical properties that conformal cyclic cosmology predicts, arguing that these features provided direct observational evidence for the previous cosmic cycle. The announcement created a sensation in the cosmology community and sparked intense debate about the validity of the claimed detection. The circles that Penrose identified were extremely subtle, representing temperature variations of only a few parts per million superimposed on the already tiny fluctuations in the cosmic microwave background. Multiple independent research groups quickly began their own analyses of the same data, trying to verify or refute Penrose's claims. The results were mixed and highly controversial. Some groups found similar circular patterns, but argued that they were consistent with random noise and statistical fluctuations in the CMB data. Others developed more sophisticated statistical tests and concluded that the observed patterns were not significantly different from what would be expected in a standard single-cycle universe. The debate intensified when the European Space Agency's Planck satellite began releasing even more precise measurements of the cosmic microwave background. Planck's superior angular resolution and sensitivity should have made it easier to detect the circular patterns that Penrose claimed to see in the earlier WMAP data. Penrose and his collaborators analysed the Planck data and continued to claim detection of the concentric circles, but their results remained highly disputed. The majority of cosmologists remained skeptical, arguing that the statistical significance of the claimed detections was not compelling enough to overturn the standard cosmological model. The controversy highlights one of the fundamental challenges in searching for pre-Big Bang signatures. The signals that cyclic theories predict are often extremely weak, buried in noise and systematic effects that can mimic genuine cosmic signatures. Distinguishing between real evidence for previous universes and statistical artifacts requires extraordinary care and sophisticated analysis techniques. But Penrose's Hawking points aren't the only potential signatures of cosmic cycles that theorists have proposed. Loop quantum cosmology models predict their own distinctive patterns in the cosmic microwave background that would result from the quantum bounce that replaced the classical Big Bang singularity. During the quantum bounce phase, the fundamental quantum geometry of space would create correlations between different regions of the universe that would persist into the subsequent expansion phase. These quantum correlations should appear as specific patterns in the CMB temperature and polarization maps that differ subtly but measurably from the predictions of standard inflation theory. The key signature involves what cosmologists call non-Gaussianity, deviations from the simple random pattern that inflation theory predicts for CMB fluctuations. Standard inflation produces fluctuations that follow a Gaussian or bell curve distribution. But quantum bounces should introduce subtle correlations that create small but detectable deviations from this pattern. Several research groups have searched for these non-Gaussian signatures in both WMAP and Planck data. The results have been tantalizing, but not yet conclusive. Some analyses have found hints of the types of correlations that loop quantum cosmology predicts, but the statistical significance remains marginal and alternative explanations cannot be ruled out. The polarization of the cosmic microwave background provides another potential window into pre-Big Bang physics. During a quantum bounce, the intense gravitational fields would generate primordial gravitational waves with characteristic properties that differ from those produced during standard inflation. These primordial gravitational waves would leave their imprint on the polarization pattern of the CMB photons, creating what cosmologists call B-mode polarization. The specific pattern of B-modes depends on the detailed physics of cosmic creation, potentially allowing us to distinguish between different theories of the universe's origin. The detection of primordial B-modes has been one of the holy grails of observational cosmology for decades. Several ground-based and balloon-borne experiments have been searching for these polarization signatures, but the signals are extremely weak and easily contaminated by foreground emission from our own galaxy. In 2014, the BICEP-2 experiment announced the detection of B-mode polarization that appeared to confirm the existence of primordial gravitational waves from inflation. The discovery was hailed as a breakthrough that provided direct evidence for the inflationary theory of cosmic origins. However, subsequent analysis revealed that the BICEP-2 signal was likely contaminated by polarized dust emission from the Milky Way galaxy rather than genuine primordial gravitational waves. The claimed detection was retracted, highlighting the extreme difficulty of separating genuine cosmic signals from foreground contamination. Despite this setback, the search for primordial B-modes continues with increasingly sophisticated experiments and analysis techniques. Future missions, like the proposed CMB Stage 4, ground-based observatory and space-based concepts like PICO, could have the sensitivity needed to detect the subtle polarization signatures that different cosmic creation theories predict. Ekpyrotic models make their own distinct predictions about what we should observe in the cosmic microwave background. The collision between brains that creates each Big Bang should produce gravitational waves with a very different spectrum from those generated by inflation or quantum bounces. In the ekpyrotic scenario, the approach phase before each brain collision would generate gravitational waves through the relative motion of the brains in higher dimensional space. These waves would have a nearly scale invariant spectrum, meaning they would have similar amplitudes at all wavelengths, but with subtle differences from the inflation prediction. The spectral index that characterizes the wavelength dependence of these gravitational waves could potentially be measured through precise observations of CMB polarization. If the observed spectral index matches the ekpyrotic prediction rather than the inflation prediction, it would provide strong evidence for the brain collision model of cosmic creation. Another potential signature of ekpyrotic cycles involves the transfer of information between colliding brains. Some versions of the theory predict that certain types of matter and energy can survive the brain collision and influence the properties of the new universe. This could create correlations between the matter distribution in our current cycle and the final state of the previous cycle. These matter transfer effects might be observable as unusual patterns in the large-scale structure of the universe or anomalous properties of dark matter and dark energy. The distribution of galaxy clusters, the cosmic web of dark matter filaments, and even the properties of dark energy itself might retain subtle influences from the previous cosmic cycle. Several observational studies have claimed to find large-scale anomalies in the cosmic microwave background and galaxy distributions that could potentially be explained by cyclic effects. The cosmic dipole, an unusual asymmetry in the CMB temperature across the sky, has been interpreted by some researchers as evidence for bulk motion of our local universe relative to a larger cosmic structure. Similarly, the cosmic cold spot, a large region of the CMB that appears significantly colder than average, has been proposed as a potential signature of cosmic topology effects or interactions with other universes. While conventional explanations involving cosmic voids or statistical fluctuations are more widely accepted, cyclic theories offer alternative interpretations for these anomalous features. The alignment of low multipole moments in the CMB power spectrum has also attracted attention as a potential signature of cosmic cycles. These large-scale patterns in the CMB temperature map appear to be correlated in ways that seem statistically unlikely in a standard single-cycle universe. Some researchers have proposed that these alignments could result from the geometry of cosmic transitions between cycles. The specific pattern of correlations might depend on the detailed mechanism that connects one cycle to the next, potentially allowing us to distinguish between different cyclic theories. However, all of these claimed detections remain highly controversial within the cosmology community. The statistical significance of the observed anomalies is often marginal, and the possibility of systematic errors, instrumental effects, or simple cosmic variance cannot be definitively ruled out. The challenge of detecting pre-Big Bang signatures is compounded by the fact that any information from previous cycles would be severely diluted by the expansion of space and the passage of cosmic time. Signals that were strong during the cosmic transition would be stretched and weakened by billions of years of cosmic evolution. Moreover, the standard cosmological model based on inflation and a single Big Bang provides excellent fits to most observational data. Any claimed detection of cyclic signatures must not only be statistically significant in its own right, but must also explain why the standard model works so well for the vast majority of observations. Future observational programs are being designed with the specific goal of searching for pre-Big Bang signatures with unprecedented sensitivity and precision. The proposed Cosmic Origins Explorer mission would map the CMB polarization with sensitivity levels that could definitively detect or rule out many of the signatures that cyclic theories predict. Ground-based experiments like the Simons Observatory and CMB Stage 4 will provide complementary measurements with different systematic error patterns, allowing for robust cross-checks of any claimed detections. The combination of space-based and ground-based observations could provide the definitive test of whether pre-Big Bang signatures are really hidden in the cosmic microwave background. Advanced gravitational wave detectors also offer new possibilities for probing the pre-Big Bang universe. The proposed space-based detector LISA will be sensitive to gravitational waves from cosmic strings, primordial black holes, and other exotic sources that might have originated in previous cosmic cycles. Even more futuristic concepts involve using quantum interferometry to detect the stochastic gravitational wave background from cosmic inflation or quantum bounces. These ultra-sensitive detectors could potentially measure the gravitational wave signatures of cosmic creation itself, providing direct evidence for the specific mechanism that triggered our Big Bang. The search for pre-Big Bang signatures represents one of the most ambitious observational programs in the history of science. We're attempting to detect the faint echoes of universes that existed before our own Big Bang, using the most sensitive instruments and sophisticated analysis techniques that human technology can provide. Success would revolutionize our understanding of cosmic origins and our place in the universe. If we could confirm that our Big Bang was just the latest episode in an eternal cosmic cycle, it would fundamentally change how we think about time, causality, and the nature of existence itself. But even negative results would be scientifically valuable, helping to constrain the properties of dark energy, quantum gravity, and the fundamental structure of space-time. Whether we detect pre-Big Bang signatures or confirm their absence, we're pushing the boundaries of human knowledge into realms that seemed forever beyond our reach. As we'll discover in our final chapter, the implications of cosmic cycles extend far beyond physics and astronomy. If the universe really does die and resurrect itself in an endless rhythm, it raises profound questions about meaning, purpose, and humanity's ultimate destiny in a cosmos that never truly ends. We began this cosmic journey with a simple question that turned out to be anything but simple. Could the Big Bang happen again? After exploring the cutting-edge theories of modern cosmology, diving deep into the mysteries of dark energy and quantum gravity, and examining the subtle clues hidden in the cosmic microwave background, we find ourselves facing an answer that's both humbling and profound. The truth is, we don't yet know for certain, but we're closer than ever to finding out. What we've discovered along the way is that this question touches the very foundations of physics, philosophy, and our understanding of existence itself. The universe we thought we knew, with its clear beginning 13.8 billion years ago and its seemingly inevitable march toward heat death, might be far stranger and more wonderful than we ever imagined. The evidence we've examined paints a picture of a cosmos balanced on a knife's edge between eternal expansion and cyclic rebirth. Dark energy, that mysterious force that makes up over 2/3 of everything that exists, could be the key that determines which fate awaits us. If dark energy remains constant forever, our universe will expand and cool until the last star burns out and the final black hole evaporates, leaving nothing but empty space, growing ever larger and colder throughout eternity. But if dark energy is dynamic, if it can change its properties over cosmic time, then everything changes. The accelerating expansion that dominates our universe today could slow down, stop, and reverse, pulling everything back together in a big crunch that might trigger the next cosmic cycle. The universe could be like a vast cosmic heart, beating with a rhythm that spans hundreds of billions of years, expanding and contracting in an eternal dance of death and rebirth. The theoretical frameworks we've explored offer multiple pathways for cosmic cycles to occur. In the ekpyrotic scenario, our universe is just one of many three-dimensional surfaces floating in higher dimensional space, periodically colliding with parallel universes in cosmic crashes that create new Big Bangs. Each collision resets the cosmic clock, wiping away the accumulated entropy and complex structures from the previous cycle and starting fresh with hot, dense matter and radiation. Picture this extraordinary scene playing out in dimensions we cannot see or directly experience. Two vast, flat universes, each containing hundreds of billions of galaxies with their countless stars and planets, slowly approaching each other through higher dimensional space, over timescales that dwarf the current age of our cosmos. The collision, when it finally occurs, releases energies so enormous that they make our Big Bang look like a firecracker compared to a nuclear bomb. Yet this violence is also creation, the moment when new space-time is born and fresh possibilities emerge from the cosmic rubble. Roger Penrose's conformal cyclic cosmology suggests an even more elegant possibility. In his vision, the infinite future of our universe, when all matter has decayed and only massless particles remain, becomes mathematically equivalent to the beginning of a new cosmic cycle. The end becomes the beginning through a conformal transformation of space-time that preserves the essential geometric structure while rescaling everything to cosmic proportions. Imagine the universe in the far distant future, perhaps 10 to the power of 100 years from now. Every star has burned out, every planet has been consumed or flung into the depths of space. Every black hole has evaporated through Hawking radiation. What remains is a vast, cold, empty expanse filled only with photons and other massless particles traveling at the speed of light. From the perspective of these particles, time has no meaning. They exist in an eternal now that spans infinite distances instantaneously. This timeless state, Penrose realized, is mathematically identical to the conditions just after the Big Bang, when the universe was so hot that all particles behaved as if they were massless. Through an elegant mathematical transformation, the infinite future of one aeon becomes the fiery beginning of the next, creating an eternal cycle that has no true beginning or end, only endless transformation. Loop quantum gravity offers perhaps the most radical reimagining of cosmic origins. In this framework, the Big Bang wasn't really a beginning at all, but a big bounce, a moment when a previous universe reached maximum compression and rebounded into the expansion phase we observe today. The quantum structure of space itself prevents the formation of singularities, replacing the classical Big Bang with a smooth quantum transition from contraction to expansion. The bounce occurs at densities so extreme that matter and energy are compressed beyond anything we can imagine in our everyday experience. At these quantum scales, space itself becomes granular, made up of discrete units that cannot be subdivided further. When the universe reaches this fundamental quantum limit, it's like a cosmic spring that has been compressed to its maximum extent. The quantum geometry of space creates a repulsive force so powerful that it reverses the collapse and drives the universe into a new phase of expansion. Each of these theories makes specific, testable predictions about what we should observe in our universe if cosmic cycles are real. The cosmic microwave background radiation, our most ancient source of information about the early universe, might contain the fossilized imprints of previous cosmic cycles. Subtle patterns in temperature and polarization could reveal the quantum signatures of cosmic bounces, the gravitational wave echoes of brane collisions, or the conformally transformed remnants of black holes from previous aeons. The search for these signatures represents one of the most ambitious scientific endeavors in human history. We're attempting to detect the faint whispers of universes that existed before our own Big Bang, using instruments so sensitive they can measure temperature differences of less than a millionth of a degree across the cosmic sky. It's like trying to hear the echo of a conversation that took place in a distant room billions of years ago, with the sound having traveled through countless obstacles and transformations along the way. Some researchers claim they've already found hints of these pre-Big Bang signatures in existing data. The concentric circles that Penrose identifies in the cosmic microwave background, the non-Gaussian correlations that could indicate quantum bounces, and the large-scale anomalies that might reflect cyclic topology effects all represent tantalizing clues that our universe might not be the first. The controversy surrounding these claims highlights just how challenging it is to extract definitive evidence from data that's inevitably contaminated by noise, systematic errors, and our own cognitive biases. The patterns are real, but their interpretation remains hotly debated. Are we seeing the echoes of previous universes, or are we falling victim to the human tendency to find patterns in random noise, like seeing faces in clouds or hearing voices in static? But science demands extraordinary evidence for extraordinary claims, and the cosmic community remains divided about whether these subtle signals represent genuine discoveries or statistical artifacts. The debate itself is healthy and necessary, reflecting the rigorous skepticism that drives scientific progress. Every claimed detection must be independently verified. Every statistical analysis must be scrutinized for errors, and every alternative explanation must be carefully considered. Future observations will likely settle these debates one way or another. The next generation of cosmic microwave background missions, with their unprecedented sensitivity and precision, should be able to definitively detect or rule out many of the signatures that cyclic theories predict. These instruments will map the cosmic sky with angular resolution and temperature sensitivity that would have seemed impossible just a few decades ago. Advanced gravitational wave detectors will probe the universe's expansion history in entirely new ways, potentially revealing the gravitational wave backgrounds from cosmic inflation, quantum bounces, or brane collisions. The space-based detector LISA, scheduled for launch in the 2030s, will be sensitive to gravitational waves from sources across cosmic history, opening a new window into the universe's most violent and energetic events. Even more futuristic concepts involve using quantum interferometry to detect the stochastic gravitational wave background from cosmic creation itself. These ultra-sensitive detectors could potentially measure the gravitational signatures of quantum space-time fluctuations, providing direct evidence for the specific mechanism that triggered our Big Bang and any previous cosmic cycles. But even as we await these observational breakthroughs, the theoretical implications of cosmic cycles continue to challenge our most basic assumptions about time, causality, and existence. If the universe is truly cyclic, then our concepts of beginning and end lose their meaning. There was no first moment, and there will be no final moment, only an eternal present that encompasses all possible pasts and futures. This perspective fundamentally changes how we think about history and progress. In a linear universe with a definite beginning and end, there's a sense of cosmic narrative, a story arc that moves from simple beginnings toward complex endings. But in a cyclic universe, history becomes circular rather than linear. Every event that has ever occurred will occur again, not just once, but infinitely many times, with infinite variations. In such a cyclic cosmos, every configuration of matter and energy that's physically possible will eventually occur, not just once, but infinitely many times. This includes not only our current universe with all its galaxies, stars, and planets, but exact duplicates of our solar system, our world, and even ourselves. Somewhere in the infinite cycles of cosmic history, there have been and will be countless versions of Earth, with their own versions of human civilization, their own Shakespeares and Einsteins, their own triumphs and tragedies. The implications are both comforting and terrifying. Death becomes just a transition to the next cycle, but so does every moment of suffering and joy. Every word you've ever spoken will be spoken again. Every choice you've ever made will be made again, along with every possible alternative choice that quantum mechanics and chaos theory allow. You are not just living one life, but infinite lives across infinite cycles, experiencing every possible variation of your existence. This eternal recurrence, as philosophers have called it, raises profound questions about free will, moral responsibility, and the meaning of individual actions. If everything that can happen will happen infinitely many times, does anything we do really matter? Or does it matter infinitely much, since our actions will be repeated and magnified across endless cycles of cosmic time? The cyclic universe also offers a potential solution to some of the deepest puzzles in cosmology. The fine-tuning of physical constants that seems necessary for the existence of stars, planets, and life could be explained not by divine intervention or infinite parallel universes, but by the fact that we naturally find ourselves in a cycle where the constants happen to have life-friendly values. This anthropic explanation suggests that the universe cycles through different configurations of physical laws and constants. Most cycles might be barren and lifeless, with physics that doesn't allow for the formation of complex structures. But occasionally, purely by chance, a cycle would have constants that permit stars to shine, planets to form, and life to evolve. We find ourselves in such a cycle not because it was designed for us, but because only life-friendly cycles can produce observers capable of asking these questions. The arrow of time, the fundamental asymmetry that distinguishes past from future, takes on new meaning in a cyclic cosmos. Rather than being a consequence of the universe's initial conditions at the Big Bang, the arrow of time might be reset with each cosmic cycle, emerging anew from the quantum processes that drive cosmic transitions. This suggests that time itself might be cyclical rather than linear, flowing in great circles rather than straight lines. The far future of our universe could literally become the distant past of the next cycle, creating closed loops in time that challenge our ordinary notions of causality. Past and future become relative concepts, meaningful only within individual cycles, but losing their absolute significance in the eternal cosmic dance. Perhaps most profoundly, cosmic cycles challenge our understanding of information and memory. In a universe that dies and is reborn, what happens to the information contained in complex structures like stars, planets, and living beings? Is it truly destroyed during cosmic transitions, or does it survive in some transformed state that could potentially be recovered in future cycles? Quantum mechanics suggests that information cannot be destroyed, only scrambled or hidden. This principle, known as unitarity, is one of the most fundamental rules governing quantum systems. If the universe is truly quantum mechanical at its deepest level, then the information that describes our current cosmic state might be preserved across cosmic transitions, encoded in subtle correlations that survive the apparent destruction of macroscopic reality. The quantum information that describes our current universe might be preserved in the fundamental structure of space-time itself, stored in higher dimensional degrees of freedom that transcend individual cosmic cycles. Each new cycle would begin not with a completely blank slate, but with quantum correlations that encode the history of all previous cycles, like a cosmic hard drive that remembers everything while appearing to forget. This quantum memory could manifest in observable ways, creating patterns in the cosmic microwave background, the large-scale structure, or the fundamental constants that reflect the accumulated history of cosmic evolution. We might be seeing not just our own universe's baby picture when we observe the CMB, but a palimpsest that contains faint traces of all previous cosmic cycles. The search for cosmic cycles also connects to some of the most speculative ideas in modern physics. String theory's landscape of possible universes, with its 10 to the power of 500 different vacuum states, suggests that there might be an almost infinite variety of possible universes, each with its own laws of physics and fundamental constants. Eternal Inflation's multiverse of bubble universes proposes that our observable universe is just one bubble in an infinite foam of expanding space-time regions, each with its own Big Bang and cosmic history. Many worlds quantum mechanics suggest that reality branches into countless parallel timelines, with every quantum measurement, creating an ever-growing tree of possible histories. Cyclic cosmology adds another layer to this already mind-boggling tapestry of possibilities. Not only might there be infinite parallel universes and infinite quantum branches, but each universe might exist in infinite temporal incarnations, cycling through death and rebirth in an endless cosmic symphony. The multiverse becomes not just a collection of parallel realities, but a vast library of cosmic histories, with each possible universe playing out its story across infinite cycles. This perspective challenges our most basic notions of uniqueness and specialness. We are not just one species on one planet, in one galaxy, in one universe. We are one instance of infinite instances, one note in an eternal cosmic composition that plays out across scales of space and time that dwarf human comprehension. Yet far from making us insignificant, this cosmic perspective might actually enhance the meaning and importance of our existence. In a universe where every possible story is told infinitely many times, consciousness becomes the narrator that gives meaning to the cosmic tale. We are not just passive observers of the cosmic drama, but active participants whose choices and experiences contribute to the infinite richness of reality. As we stand at this cosmic crossroads, poised between the known and the unknown, we're reminded of how much mystery still surrounds us. The universe that seemed so well understood just a few decades ago has revealed itself to be far stranger and more complex than we ever imagined. Dark energy, dark matter, quantum gravity, and higher dimensions all represent frontiers where our current knowledge fades into speculation and hope. The question of cosmic cycles sits at the intersection of all these mysteries, requiring breakthroughs in multiple areas of fundamental physics before we can hope to answer it definitively. We need to understand the true nature of dark energy and whether it can evolve over cosmic time. We need a complete theory of quantum gravity that can describe what happens at the extreme densities and temperatures of cosmic creation. We need to unravel the structure of higher dimensions and determine whether they play a role in cosmic evolution. But that's what makes this such an exciting time to be alive and curious about the cosmos. We're living at a moment when humanity is developing the theoretical frameworks and observational tools needed to probe these ultimate questions about the nature of reality. Whether through advanced gravitational wave detectors, quantum computers, space-based telescopes, or technologies we haven't yet imagined, we're building the instruments that could reveal whether we live in a universe that began once and will end forever, or in a cosmos that has been dancing this cosmic dance since before time began. The implications extend far beyond science into philosophy, religion, and our understanding of humanity's place in the cosmic order. If the universe is cyclic, then we're not just temporary arrangements of atoms in a cosmos rushing toward heat death. We're participants in an eternal cosmic story, with every action and choice resonating across infinite cycles of time. This eternal perspective might fundamentally change how we approach moral and ethical questions. If our actions have consequences that extend across cosmic cycles, then the responsibility we bear for our choices becomes truly cosmic in scope. The love we share, the beauty we create, the knowledge we discover, and the suffering we alleviate might all echo through infinite future cycles, making every moment of compassion and every act of creation cosmically significant. Whether the cosmos will reboot remains one of the greatest unsolved mysteries in science. But as we've seen throughout this journey, the question itself has already transformed our understanding of space, time, matter, and energy. By daring to ask whether the Big Bang could happen again, we've opened new windows into the fundamental nature of reality and our place within it. The universe may or may not be cyclic, but our quest to understand it is ongoing and eternal. Each new observation, each theoretical breakthrough, each moment of cosmic wonder brings us closer to answering the ultimate questions about our origins and our destiny. In a cosmos that might be eternal, that quest for understanding becomes not just a scientific endeavor, but a cosmic imperative that connects us to the deepest rhythms of existence itself. The next few decades promise to be revolutionary for our understanding of cosmic cycles. Advanced detectors will probe the universe with unprecedented sensitivity. Quantum computers will simulate cosmic evolution in ways never before possible. Artificial intelligence will discover patterns in cosmic data that human minds might never notice. The convergence of these technologies could finally answer the question that has driven our entire journey. So the next time you look up at the night sky, remember that those points of light might not just be remnants of our universe's birth. They might be harbingers of universes yet to come, eternal beacons in a cosmic cycle that has no beginning and no end. In such a universe, every ending is also a new beginning, and the cosmic story continues forever, with each chapter more wondrous than the last. The cosmos might indeed reboot again and again.